Alright, welcome back. In the last video, I told you about the fundamental theorem of calculus for line integrals, which allows us to evaluate a line integral of a gradient function by looking at the potential function evaluated at endpoints. Remember, a potential function, it's kind of like an antiderivative. It's the function whose gradient is our vector field. So if we're going to use this to help us evaluate a line integral, we need to be able to basically undo a gradient. We can look at our integral and we want to ask, oh, what's the function f whose gradient gets us there? So again, that's called the potential function. So if we've got a vector field, f, how do we find the potential function? Here's how we can begin. If the vector field f is indeed equal to a gradient of some real value function little f, then, well, in particular, the partial with respect to x of little f is equal to y. That's the first component of the vector field capital F. And the partial with respect to y is x plus 1. That's the second component of our vector field, right? That's how we make a gradient. So what we can do is anti-differentiate. If the partial with respect to x is y, let's undo that operation. That is, we'll anti-differentiate with respect to x. And we'll get, well, y times x. Y is just like a constant as far as x is concerned, plus a constant. But now this constant, keep in mind, is constant with respect to x. It could involve y. So to make sure that we don't forget that, let me write it as a function c of y, which, again, can't involve x, but could potentially involve y. So again, little f, the potential function, has to be of this form. And now you might be tempted to do the same thing with this equation, anti-differentiate with respect to y, and then compare the two answers. But here's a way that's a little more systematic. Let's take our new expression and differentiate with respect to y. You'll see why we'll do this. If we differentiate with respect to y, well, over here this is f, so differentiating gets us the partial derivative of f with respect to y. And if we do that partial differentiation, we get x plus c prime y. But the partial with respect to y is also x plus 1. Right? And that's what we got above, because it's part of the gradient. So putting it together, we would need x plus c prime of y to equal x plus 1. Or we can cancel the x's and say c prime of y has to be 1. And now, one more time, anti-differentiate, this time with respect to y, and say, well then, c of y has to be y. Y plus a constant, maybe let's call it d, we've already used c. And this constant is a legit constant, meaning it doesn't depend on x or y. So an actual honest constant. So putting it all together now, we said f was yx plus this function c of y. Now we know what is that function c of y. So we'll put it all together. And we get that f of xy is yx plus, and our function c of y is y, plus some constant d. And you can check that, yes, if you take the gradient of this function, you'll definitely get to where we started. Let's try with another. So here, our function f, capital F, is the gradient, the vector field minus yx. Again, we can say that if it's a gradient, then the partial with respect to x has to be minus y, the partial with respect to y has to be x. We can do all the same steps, anti-differentiate with respect to x, and see something very similar to the last one. This seems to imply that f should be minus xy plus some constant that can depend on y. We can take a partial with respect to y, I should use the partial symbol, not a d, and get that this is minus x plus c prime of y. Specifically, this should be equal to the partial of f with respect to y, since this is f, and we took a derivative. But now if you compare to what we saw above, this is trouble. Both of these things can't be true at the same time. We can't have a minus x and an x. This function can only depend on y, so it can't do anything to make this minus x look more like an x. So we might suspect that this is not a conservative vector field. Remember, that means path independent, which we said was the same as being a gradient function. So it turns out that this vector field does not have a potential function. We haven't proved it yet. Basically what we found is that we're having trouble finding one. But let's check this out. If big F is a gradient vector field, then, as we said above, fx is equal to minus y and fy is equal to x. But by Clairaut's theorem, remember this is the one that says that the mixed partials should be the same. And we can check here that they're not. fxy is minus 1, but fyx is 1, and these are clearly not the same. So if it were a potential vector field, if we had a potential function, then these should be the same. They're not, so it can't be, it can't have a potential function. So in the next video, it'll be a short one. We will use these ideas to actually apply the fundamental theorem of calculus for line integrals.